So we did radiative balance for Earth, and I think we mentioned Venus being very hot and Mars being very cold compared to Earth, and Mars can be explained by the distance from the Sun, its size, its greenhouse gases, but Venus is much warmer because of the runaway greenhouse effect, and whatever radiation balance model you make, it has to work for all the planets on the solar system to prove that your science is because the science is solid, not to prove it. Obviously the science has to give you the right answer for all the planets, not just for Earth, even though it is done in a one-dimensional way and there are details which matter, as we already saw, which we will see again. So here we are looking at energy emitted in terms of wavelengths of microns by two hypothetical stars. So star A is here and star B is here, and we have already talked about the Planck's curve and the Wien's law and so on about maximum wavelength relation to temperature, etc. You can imagine that the shorter wavelength here and energy emitted distribution is very different here. So it's emitting in a much shorter wavelength, whereas this one is emitting in a much larger range of longer wavelengths as well. So we saw the Sun and Earth, but here we are talking about two planets. But we can just come back to thinking about the planet with simple atmosphere or no atmosphere. When we did energy balance with no atmosphere and the energy going directly from the surface to space, we found the surface temperature to be 15 degrees centigrade, which is much colder, or whatever it was, minus 18 degrees centigrade, and then when we added one layer which went to 33 degrees, and then we needed multiple layers to bring it back. So here, let's say Sun is sending net amount including the albedo loss of 238 watts per meter squared. So this is schematic of energy flow on a planet with one layer atmosphere. The atmosphere is represented by a single layer that is transparent to visible photons. So solar energy here is coming back, coming all the way to the surface, but absorbs all of the infrared photons that fall on it, which is the assumption we had made as well. The arrows show global energy, average energy flows with values in watts per meter squared. So without even worrying about how much got lost by albedo, if surface is receiving 238 and the surface will emit that energy, but it won't go to space because the atmosphere is completely opaque to the outgoing long wave, so it will acquire temperature, which has to send that 238 back to space, because at the top of the atmosphere we have to balance the energy for a long-term equilibrium. Planet is not warming, not cooling, it has reached some equilibrium. So then that atmosphere, as we said before, will send 238 back towards the surface as well, because the blackbody radiation is in all directions, and the surface thus is receiving now emitting 476, because it has to get rid of the 238 it received in the visible and the 238 it received in the infrared from the atmosphere. So you can see that even though total energy received is only 238 watts per meter squared, we have created a warm blanket which is increasing internally the amount of energy bouncing around to 476, right? So obviously we saw that this gives us very warm temperatures, 33 degrees centigrade. Then we increased the complexity. So looking again at, for Earth we did 30% albedo and 342 watts per meter squared at the top of the atmosphere. We reflected 30%, took some in the atmosphere into the surface, and then we did this kind of bouncing around. So here now you still have to emit 238 to space, but we have added another layer here. So we have a lower atmosphere and an upper atmosphere. So start here, surface is receiving 238, this has to emit 238. The upper atmosphere is going to send out 238 up and 238 down. Again, assume that the lower atmosphere is completely opaque to this downwelling long wave radiation. So it is going to receive 238 from the surface and 238 from above. So it's going to reach a temperature which has to get rid of 476 watts per meter squared. But that's going to bounce 476 watts per meter squared downward as well, again with the simple blackbody radiation calculation. So now the surface is essentially receiving 238 plus 476, so it has 714 watts per meter squared to get rid of, which it is sending upward, out of which this is reaching a temperature to get rid of 476, and that is going to reach a temperature where it's going to emit 238. This is the calculation we did also when we were talking about band saturation. The emission to outer space has to happen at colder and colder temperatures to match the energy coming in, and internally you begin to warm. So the first idea was that as soon as you add a layer of greenhouse gas, which is transparent, not completely transparent to outgoing long wave from the surface, you're going to bounce energy back, and the surface is going to be warmer than it would be if there was no atmosphere which has a greenhouse effect. And as you increase the number of layers, you're increasing the amount of energy coming back to the surface and the amount of energy it has to get rid of, which means it has to reach, remember, sigma T to the fourth, so it has to reach a higher temperature to produce 714 watts per meter squared back out, and this has to remain at a cold enough temperature to emit only 238. Sigma T to the fourth is 238. So we are essentially going to move the level at which energy is emitted to colder temperatures as we keep warming here, as we said before. So the band saturation argument doesn't work. But we can extend this idea here: schematic energy flow on a planet with an n layer atmosphere. Layers are numbered 1 to n with values in watts per meter squared. So we can take just 150 watts per meter squared coming in here, and we have to emit 150 here. So we can see that as there are n number of layers, the energy bounced around is going to change proportionately. So the surface has to emit 150 times n plus 1 amount of energy out, because it's going to receive this plus 150 times n coming down, and then you have 150 times n going out here, 150 times n minus 1, and so on up at the top of 150 times 1, so that you still have equilibrium, but now you have increased the contrast quite a bit. So the surface is at a temperature where it is emitting 150 times n plus 1 watts per meter squared. The temperature sigma T to the fourth you can derive from that, and here you're at a cold temperature to emit only 150 in sigma T to the fourth. So this idea comes out much more clearly when we do it this way. So you can now go back and listen to the other podcasts if you want. So essentially, surface temperature of the for the n layer planet as a function of the number of layers. Still we have the net amount of energy received is what's coming at the top of the atmosphere minus the albedo, and we are distributing it on the sphere, so you have to divide by 4 pi r squared. So that's where the 4 comes from, as you remember. So you can see that as the number of layers increases, the surface temperature does begin to saturate. So in that sense, band saturation does begin to limit how warm the surface can get, but that doesn't limit the greenhouse effect, because the layers begin to move. The top layer where the energy is released begins to rise. So right now we know that tropopause is rising around the globe because of these precise mechanisms. So you can think of this as a very simple climate model which explains exactly what's happening with global warming with exact physics, radiation, so there is no denial, there is no room for denial. Okay. So comparing now the different planets, data on the 4 inner planets in our solar system, looking at the solar constant, the amount coming in at the top of each atmosphere. Mercury is receiving 10,000 watts per meter squared with a very low albedo of 0.1. Observed surface temperature is 452 Kelvin. So inferred number of layers from using this is 0.052. Venus is receiving 2650, almost the double of what Earth receives, with an albedo that is also more than double. and its surface temperature is 735, which is warmer than Mercury. So you can see the difference. Much less energy received because of the distance from the Sun, but much warmer temperatures, and because it has essentially 82 layers which bounce the energy between them and increase the surface temperature, because surface has to get rid of a lot of energy. Earth is receiving 1360, which changes in time, as we know. Albedo, as we said, is 30% or 0.3. We have a balmy surface temperature of 289, which is just over 15 degrees centigrade, because we are warming over time. And inferred N here is 0.65. Don't get confused. This just means that the way energy is sent back to space is complicated. So the atmosphere is stratified. Surface energy is not all of it cannot go out, some of it does, and then each layer in the stratified atmosphere is sending back some energy. So the effective number of layers for the emission temperature turns out to be 0.65. That's just the physics of it. Okay. Mars receives much less energy at 580, about half of Earth. Is it? Yeah. Albedo is much lower, temperature is correspondingly lower, and it has a number of layers which are much lower at 0.22 as well. Okay, so this is the way to think about a simple climate model in the context of the energy balance we did before, and this should convince you that we are in fact very robust in our calculations, in our radiative balance understanding, and when done globally, then it's easier to ignore the internal details, the internal feedbacks, the ocean circulation, atmosphere circulation, cyclones, hurricanes, meridional overturning circulation, Hadley cell, and everything, and just look at long-term equilibrium calculations, and then it makes it easier to also understand how increasing the greenhouse gas effects effectively increases the number of layers, or the height at which the energy has to be released, and that explains why band saturation arguments don't work, and why global warming, because of greenhouse gases, is very robust, accurate, and precise science. Okay.